Module 1, Lesson 7, Muller's Method. For this module, we'll be dealing with nonlinear polynomial functions only, and iterative techniques that are used to solve nonlinear polynomial functions, such as the Muller's method. We will then show how curve-fitting parameters eventually are utilized by Muller's method, and how to derive its iterative formula. And finally, we'll answer a few sample problems. Nonlinear polynomial functions or algebraic equations normally appear in a given standard form, which is denoted like this, whereby your an corresponds to the constant coefficients of your polynomial function, and n is the degree of your polynomial function, which usually is associated with your variable x. The roots of your polynomial function depend on the value of n. The roots will either be a real number or complex conjugates. Although there are empirical formulas that evaluates the roots of your nonlinear polynomial function, still, iterative techniques are still more preferred over empirical formulas. The Muller's method is basically an iterative technique that utilizes a parabolic function in order to approximate the root of your polynomial function, which is given in this given form, whereby you have coefficient a multiplied to x minus x2 squared plus coefficient b multiplied to x minus x2 plus coefficient c, from which you can evaluate for the root value. With the use of these three initial values, x0, x1, and x2, substituted to your general parabolic function, the technique computes for coefficients a, b, and c in order to approximate the root value called x3. These initial values x0 along with their functions fx0, x1, fx1, x2, fx2 are used as initial values and are fitted onto your general parabolic function. The graphical depiction of how the technique eventually fits your given initial values to your parabola looks like this. You set off an initial value x0 with its given function, fx0, your x1 with your function fx1, and your x2 with a function fx2. From there, you apply these curve-fitting parameters that uses h0, which pertains to the distance between x1 and x0, likewise h1, which pertains to the distance between your initial value x2 and x1, as well as the difference on your function values, which are referred to as delta 0 and delta 1. They are now used to approximate your root value, which is referred to as your x3, after fitting all of these parameters onto a parabola. Upon using these initial values, your parabolic function or equation will then yield equation 1 if you substitute x0, equation 2 if you substitute x1, and equation 3 if you substitute x2. Note that on equation 3, coefficient a becomes 0, likewise coefficient b. Therefore, c is simply equal to fx2. Using this particular relation, we can simplify equations 1 and 2 to form equation 4 and equation 5. Equations 4 and 5 are then used using the curve-fitting parameters that are applied, stating the technique Newton's divided difference interpolation polynomial, which we will discuss later when dealing with curve-fitting techniques. Note that these are the curve-fitting parameters depicted in the graphical depiction, wherein h0 implies the difference between x1 and x0, h1 implies the difference between x2 and x1, delta 0 implies the slope of the straight line connecting your data point x1, x0, so which is equivalent to the difference between your function fx1 minus fx0 divided by the difference of your values of x, which is h0. And your delta 1 likewise is the slope connecting the data point x1 and x2, depicted to be the difference between fx2 minus fx1 all over the difference between x2 minus x1, or simply h1. Substituting then the parameters on your equations 4 and 5 will eventually yield to be like this. Those curve fitting parameters are then substituted and it becomes like this, your equation 4. Then this becomes your equation 5. And from your equation 5, you could actually solve your B, coefficient B. After solving for coefficient B, we then substitute this value B to your equation 4. That will eventually yield like this, simplified, and you would eventually end up with the formula for your A0, which is equivalent to delta 1 minus delta 0 all over H1 plus H0. Then a discriminant value is used to determine whether your computed root value is a complex conjugate or a real number, which is called your discriminant D, evaluated to be the square root of B squared minus 4AC, taken from the coefficients of your parabolic function. And in solving then for your root estimate x3, you simply apply this formula. Note that on this formula, your divisor operand comes with a plus or a minus. It becomes plus if the coefficient B is positive. It becomes minus if the coefficient B is negative. And then after solving for your root estimate x3, you then apply this substitution process, which is basically similar to your second method, whereby you disregard the previous value of x0, then the previous value of x1 is substituted as x0, the previous value of x2 substituted as x1, and the computed x3 substituted as x2. And then the process is repeated until the terminating condition is simply satisfied. The terminating condition states this formula, which is basically similar to your relative error, since your x3 calculated value is substituted as your x2. Therefore, this meant that x2 is the previous value of x3. Hence, if you look at the formula, it's basically like a relative error. Let's try to apply that on this given particular example, wherein we are asked to evaluate a root of the function using Muller's method and terminate if this particular criteria is satisfied. So we begin the solution by setting up initial values for x0, x1, and x2. In this case, I simply used any three initial integer values that you could use or prefer. No? On the first iteration then, you'd have this function values for your x. You could now solve for the curve fitting parameter h0, h1 using the formula. Likewise, delta 0 with this solution and delta 1 with this solution. Knowing now these curve fitting parameters, we could solve for your coefficients. A, which turns out to be 8, your coefficient B, which turns out to be 34, and note that this is positive, therefore, on our divisor operand, we will use plus. And your coefficient C, which is simply equal to fx2, which turns out to be a value of 20. Then we evaluate the discriminant D in order to determine whether our root would be a complex conjugate or a real number. If D turns out to be a complex number, then all calculations are simply reverted into a complex mode, meaning all complex numbers are best evaluated using polar form when you are multiplying them or dividing, and they are easily evaluated using rectangular form if they are in trigonometric form or the rectangular form. So your x3 can be computed to be 4.2947 for the first iteration, and the error giving us 16.4226%. On the second iteration, then we disregard x0, we substitute our x1 as x0, which turns out to be 4. Your x1 now becomes 5, and your x2 becomes 4.2947. Substituting these functions to your iterative formula would give us a curve fitting parameters h0 equal to 1 and h1 equal to negative 0.7053. A delta 0 of 26 and a delta 1 equal to 28.7391. We then evaluate our coefficient A having the formula with a value of 9.2945, B with a value of 22.1837 based from our solution. And again, since this is positive, we use plus, and a C equal to fx2, which is negative 0.2697. Your D would turn out to be the square root of b squared minus 4ac, which gives us a value of 22.4086, and an x3 now equivalent to 4.3068. With an error value of 0.2810%, meaning we need to repeat the process. So on the third iteration, we discarded x0. Our x0 now is 5, your x1 is 4.2947, and your x2 4.3068. Ending up now with the following function values and a curve fitting parameter equal to h0, which is negative 0.7053, h1, which is 0.0121, delta 0, which is 28.7391, and a delta 1 equal to 22.0826. And your coefficients to be A equal to 9.6026, B equal to 22.1988, and then it's a positive, therefore we use plus again. C equal to fx2, which turns out to be negative 0.0025, and your D turns out to have a value of 22.201 based from this solution. So we can now compute for x3 to be like this, and the root value equal to 4.3069. If we calculate for the error now is 0.0023%, satisfying our terminating condition, stating that the root for this given particular function is equivalent to 4.3069. That covers Muller's method.